Okay. You want a review class? You got it. So, review class on Wednesday. I've got more copies of the practice test, right? Remember, so what you're going to do for a freebie assignment mark, right, is you're going to attempt all of these. I don't care if you did it right or wrong, right? We'll go through them together. But what you're going to do is you're going to do the practice test before the review class. And then at the beginning of class, I'll walk around and just, you show me that you did everything, right? Again, doesn't have to be right. Just show me that you tried all these questions, right? And then we'll go through it together and I'll just mark you down as one assignment mark, 100%. Okay? So pretty easy marks. Should probably do it. Don't forget. Okay? So if you need a printout of the practice test, it's right here. And like I said, we'll go through that on Wednesday. So complete the practice test. Hopefully it's showing, yeah. The practice test and show me your work at the beginning of class to get a 100% assignment mark. Right, or completion mark. So if that doesn't make sense, then just come ask me, right? But just do it and it'll count as an assignment mark. I posted tons of Moodle assignments, right? But like I said, last day, I just did many instead of one long one, just so we could break them up. And then that way they're not worth as much each, right? So let's do a quick review. We're kind of changing gears today. We're gonna do monopolies, which are special cases. Okay? But so as far as a review goes, what did we talk about? We talked about the CVP analysis, which we decided was cost value? No, volume. Was it profit? Turned out I'd been using the wrong names for these acronyms. Doesn't matter, that's not my job. My job's to show you the formulas. Cost, volume, profit. Doesn't have the same ring to it, but thank you. Right, and so we looked at how do we use these formulas to develop profit functions, right? And so we developed profit functions given information, right? And so in general, what we said was, well, the profit of X is the total revenue minus the total cost. Right? That's where we started for most of these questions, just to develop a profit function. But then we said, well, that's not really helpful. The total revenue, we can actually replace it with PX. And we defined P. P is the price that you're able to charge per item, right? And X is the number of items that you're selling or producing. We're working as if they're the same, right? If you produce it, you sell it. Right? Not always the case, unfortunately. And the total cost, we can replace it with the variable cost plus the fixed cost. Making note of the brackets, right? Because we're minusing this whole chunk. which becomes px minus bc plus, oh, sorry, there I did it, minus fc, if we expand those brackets out. And then finally, the last thing we can replace, right, with the formulas on our formula sheet is the VC is actually C times X. So we have PX minus CX minus the fixed cost, where C is the cost to produce each item times X, however many items you're producing. And then we said, well, we can simplify this to X times P minus C minus the fixed cost. And then we did examples of this, right, where we are given this information, have to develop the profit function. And we talked about things like, what's the shutdown point? I'll just start over. The shutdown point. Right, you shut it down when P is less than C, right? When the price that you're able to charge for the item is less than the cost to produce it, you gotta shut it down, right? You can't be producing more if it costs more than what you can sell it for, right? So that's the shutdown point. And then we said, well, another point that we might be interested is the break-even point. The break-even point is where the profit is zero, right? We go from making a negative profit to a positive profit, right? So this is where the profit is zero. Right? So those are some things that we talked about last day. Any questions before we start this new stuff? Just keep it going, Emily. Got it. So today, I want to do 3.4, which is on the special case of a monopoly, right? But before we get there, we have to talk a little tiny bit about calculus. What? I know, but it won't be that bad. Okay, we're gonna do fake calculus, if you will. Okay, and so first, I'm gonna take us back to 3.1, which I said before. I'm gonna skip this and come back to it when we need it. Now we kind of need it. So we'll start in 3.1 and then go to 3.4. Okay. So let's go back to 3.1, then we can do 3.4. Just so you know what's going on. I used to really not like when profs did that, when they jumped around in sections. Like, oh, well, obviously it's over here and over here. What? So I'm giving you fair warning. 3.1 is the basics. It's called the basics. It's actually not really. It's an introduction to calculus. If you were to go ahead and read 3.1 and 3.4 in the textbook, maybe they'll make sense, maybe they won't. So I've pulled out all the information that we need to do these problems. It goes through a lot more theory and kind of what's happening in the background, right? So if you want more theory, then it's all in the textbook, but I'm just gonna give you what you need, cut out the stuff that you don't. Okay. So we will cover the basics of derivatives. So derivatives are one section of calculus, and but we're not going to do any formal definitions and no theory. Okay, so basically not at all. So we will cover the basics of derivatives but no formal definitions or theory. I'll put a note here. See textbook for some of the theory. Even the textbooks cut out a lot of the theory for some of the theory. But like I said, you don't need to. It's just if you're curious or if it's not making sense. So what's a derivative, you ask? Has anyone taken calculus? No? It's okay. I don't think you have to. So why would you? So a derivative is the slope of the tangent line of a function. What's a tangent line? Tangent line is at any point on a curve, we can pick a point, and then if we put a straight line that only touches that point, that's the tangent line. Okay? So I'll write all that out, but essentially what we're doing is we're finding the slope of the tangent line when we're finding a derivative. So first I'll define a derivative. The derivative of a function, I'll put in brackets here f of x, that's any function, is the slope of the tangent line at any value of x. So really what it's doing is it gives us another function that we can use to find the slope of the tangent line. So it gives us a function for finding the slope of the tangent line now. Of course, we have to define the tangent line. We talked about it, but the tangent line is the straight line that only touches a single point on a curve. So the tangent line is the straight line that only touches a single point on a curve. That only touches a single point on the curve. So what it looks like is if we have something like this, right, we've got our x and our y axes, and let's pretend we have a function that looks something like this. That can be our f of x. So any function, right, f could look like this if we wanted to. Probably not. Looks nasty. Right? Any sort of curve. Right? And so here, at this point, let's say here, we're at some value of x, right? Let's say here we're at x equal to a. At x equal to a, even though we can't see colors on here, there's the tangent line. It goes something like this. Right? So it's a straight line, even though it doesn't really look that straight, but it's supposed to be straight. Okay? And it only touches that one point on the curve. Right? So it's just touching, and then it's off. So here, what we have is the tangent line at x equal to a. Why do we care about the derivative, which is the slope of the tangent line? The slope of the tangent line, right, is the rise over run. Right? We kind of know that, the slope. But it's telling us how quickly things are changing at that point. And so each value of x will have its own tangent line. And also the tangent line, actually, I'll say the slope of the tangent line. That's what I should have said. Which is the derivative tells us the rate of change at each value of x. Right. How quickly is something changing there? So here, right, if you've got this curve here, then at every single point here, we're going to have a tangent line, and it's just moving incrementally all around the line. And so finding the derivative finds a function for the slope of each tangent line as we move from one x to the other. Any questions? You'll see it won't be that bad. So therefore, the derivative of f of x at x equal to a is the slope of the tangent line of f of x at x equal to a. Right, just kind of re-emphasizing. I did tell him I was in class, but maybe you didn't get it. Can't FaceTime now. Stop sharing my screen. Or maybe we do want to FaceTime. No. Don't worry. Back in action. Okay. Therefore, the derivative of f of x at x equal to a, so I'm just picking a point and calling it a, of f of x at x equal to a is the slope of the tangent line of f of x at x equal to a. Just re-emphasizing that the derivative is the slope of the tangent line. So we need some notation, right, to be able to distinguish between just the function and the derivative of that function. And so we denote the derivative of f of x by f prime of x. It's got a little apostrophe on it. Right? And you're going to read this as f prime of x. What you'll see is we'll actually be taking derivatives of a profit function. Okay? And so, or we could say the profit prime of x, right? That's going to be the derivative of the profit function. Derivative of the profit function. So that's kind of where we're headed. First, we need to know what a derivative is. How does it work? What do we do? Right? And then we'll be able to, but what we're working towards is being able to take the derivative of a profit function to maximize it. Fun. So in this course, the only derivatives that we'll do are polynomials. So if you've ever taken any derivative of anything, you probably went a little bit further than polynomials. So that's why I make you guys do it anyways, because it's pretty fun once you get the hang of it. So in this course, we only need to be able to find the derivative of a polynomial. What's a polynomial, you ask? Or maybe you know. Example of a polynomial is something like f of x is 3x to the 4 plus 6x to the 3 plus x squared, squared, plus 3. Right. Nothing crazy. It's just got some x's of different powers, and that's it, right? And some coefficients, and they're either being added or we'll see some subtraction in there, right? But it's just a series of x's with coefficients. And we've seen stuff like this already. So that's a polynomial. Okay. This is actually a polynomial degree 4, and the reason it's degree 4 is because the highest power of x is 4. And what we'll be doing, we'll deal with things as big as degree 2. It's not that bad. Wah, wah. But once you know how to do one, right, find the derivative of a polynomial, you can find any degree. So, or in general, we can say something like P of X. And I used to start with this definition and then show you a real one. Right? But if I had to write this function out in general, right, I would have to have a spot for the coefficient, right? Each one has its coefficient, right? And then there's an X with a power, right? And so in general, what I can write is something like a subscript n times x to the n, right? Because in general, I'm leaving room for n degrees, right? Could be 100, could be 50, could be 10,000. No, well, it can be. That'd be tough though. Okay. But so we just use the n as a placeholder. And then we move down one to a subscript n minus 1 times x to the n minus 1 plus, and then just some dots to indicate that the same thing happens over and over again as we're slowly decreasing the power as we go through, right? Decreasing the power by n each time. 1 each time, sorry. Until we hit a subscript 1 x to the power of 1 plus a subscript 0 x to the power of 0. So here's a fact or facts. First one, all the a's are just placeholders for coefficients, right? So all the a's are placeholders for coefficients. Over here at the end, right, I've got a sub 0 times x to the power of 0. X to the power of 0 is just 1. In fact, anything to the power of 0 is 1. Anything to the power of 0 is 1. And x to the power of 1, we can just rewrite as x. It's a little bit cleaner, right? So what we can do is we can clean up this general function a little bit, especially the tail end, right? And just do a subscript 1x plus a subscript 0, because it's just times 1, right? So in general, what we have is, oops, p of x, that's too low. P of x is a subscript n times x to the n. So that's the same, the second one's the same too, a subscript n minus 1 times x to the n minus 1. Plus, here's where we get to tidy up a little bit and say a subscript 1x plus a subscript 0. The derivative of p of x is, I'm just going to give it to you, p prime of x, right, to indicate that here comes the derivative. We're going to write it out and then talk about it. We still have the a subscript n. That's going to be there still. But what happens is we bring down the power and then decrease the power by 1. Okay. So what I mean by that is you have a subscript n times x to the n minus 1. So if you just zoom in on this little guy, right, ignore the rest. What I imagine doing is I imagine just bumping it from this side, right, from the right-hand side. I just give it a bump, and then the n falls down in front and multiplies the coefficient, and then it gets decreased by 1. Right. Now what we do is we do that to the whole thing, right, and they just do it individually. Okay. I have to do the general version first, but then I'll do an example, and I think it'll make a little bit more sense. Okay. So again, we still have this coefficient a n minus 1 times n minus 1, because that got bumped down, times x to the n minus 1 minus 1. Plus a subscript 1. Here it helps to remember that x is actually x to the power of 1. So if we bring down that power of 1 times x to the 1 minus 1, that makes x to the power of 0, right? Oh, and then I don't have room, so I'll have to sneak it here. We've got a sub 0 times, it's not multiplied by an x, right? So it's really multiplied by x to the power of 0. So when we bring down that 0, x to the power of 0 minus 1, technically. But here, let's write down some facts. A subscript 1 times x, actually, the derivative of a subscript 1 of x is a subscript 1. So if you've got a coefficient multiplying just an x, the derivative will only leave you with the coefficient. Right, so if you have a coefficient to a single x, the derivative is just the coefficient. Second fact, the derivative of a constant is 0. Okay. If you think about it this way, right, a constant would just be a straight line like this, right? So there is no change as you move, right? And so the derivative, right, is it's telling you the rate of change at each value. There's no change for a constant. And so the derivative of a constant is 0. So like I said, there are, of course, technical ways of finding these things. There's lots of theorems and stuff that we could go through. We're not going to, it's not worth it, because we only need it for this little section and then we don't need it ever again in this course. So just today, one-time deal. Well, and on test 1. But I don't think it's on, I don't have it on the final. So that's nice. Right? So just test 1, I guess. Let's just say there are technical ways, of course. In fact, it's the whole or half of the field of calculus. There are technical ways of finding the derivative of a polynomial. But here I'm going to write down what I do, right? And hopefully it makes sense to you, because I just imagine giving it a bump from the right-hand side. Everything just kind of falls down and decreases by 1. You'll see in the example. But I imagine giving my function a bump from the right, making the powers fall down, making the powers fall down, as they fall down, right, they're going to multiply the by the existing coefficient to multiply with the existing coefficient and decreasing the powers by 1. And decreasing the powers by 1. I'll show you what I mean in an example. Hopefully it'll be a little bit better. So if f of x, let's do that 3x to the 4 plus 6x to the 3 plus x squared plus 3, find f prime of x. So then f prime of x here's where I imagine just giving it a bump. And what's going to happen is this 4 is going to fall down in front. And so now the coefficient is 3 times 4, right? Because it's fallen down in front. And because it fell down, you have to decrease it by 1, right? So it becomes 3 times 4 times x to the power of 3. Right? And so what we're doing when we're finding the derivative is we actually decrease all the powers by 1. So this one here, we can move on and say, well, this 3 would get bumped down in front. So we have 6 times 3 times x to the power of 2 now. Same thing here. Technically, we have 1 times x squared. This 2 gets bumped down in front here. So we have 2x to the power of 2 minus 1 is 1. 3, there is no x, right? The derivative of a constant is 0. And that's what we wrote earlier. So what we have is we have 3 times 4 times x to the power of 4 minus 1 plus 6 times 3 times x to the power of 3 minus 1 plus, I'll just do the 2, right? 1's kind of invisible. 2 times x to the power of 2 minus 1 plus 0. So we can simplify this and say, well, that's the same as 12x to the power of 3 plus 18x squared plus 2x. So when we take the derivative of a polynomial, it actually becomes simpler, right, than the original. We had x to the 4 as our highest power. Now x to the 3 is our highest power. It's easier to deal with. So if you wanted to, right, because a lot of people, once you get the hang of it, if you just want to go from here to here, that's fine, right? I'm just showing you that first step so you can see what's going on, right? But later on, as you get more comfortable, if you want to just jump to this line, that's fine. Okay. Any questions about that one? We'll see more examples, but. So what this is giving us, right? F prime of x is the function, right? Because it itself is a function, right? For finding the slope of the tangent line at some value of x. So F prime of x is the function for finding the slope of the tangent line of f of x at x equal to a by finding, and here's the trick, the derivative of f at a. So as another example, or actually it's just a continuation of that example. Sorry, looks different, but it's the same. What is the slope of the tangent line at x equal to 2, for example? So what is the slope of the tangent line of f of x is, and I'm just using that same f of x as before, 3x to the 4 plus 6x to the 3 plus x squared plus 3, just so you can see it through. So what is the slope of the tangent line of f of x is this at x equal to 2? Well, first we have to find the derivative. Right? F prime of x is, and what we said was it was 12x to the 3 plus 18x squared plus 2x. We already found it. So then f prime at 2, to find the slope of the tangent line at x equal to 2, you can plug in x equal to 2 into the derivative. So 12 times 2 to the 3 plus 18 times 2 squared plus 2 times 2. is 12 times 8. I'll show all my work just so you can kind of follow through. 8 times 4 plus 4. So we get 96 plus 72 plus 4 is 172. So the slope of the tangent line at x equal to 2 is 172. And that just tells us how quickly things are moving on this line. Why do we care about this? So, like I said, this is only for this very special special case. Hey, here's a nice function. Whoa. We won't deal with stuff like that. Looks more like geography, but that's also a function. Functions are everywhere. So we care about this because in a monopoly, the profit function looks a little bit different than what we're used to, right? We're used to seeing these linear profit functions where, you know, we produce more, we sell more, we make more, and it just keeps going up and up. The only thing that's putting a stop on it is the demand, right? At some point, people aren't going to want your product anymore. Right? But we're used to these linear profit functions, and that's nice. But here, so in a monopoly, the profit function looks like this. So we'll have the profit on the y-axis and x on the x-axis. And the profit function looks like this. I didn't mean to start. Just looks like a bow like that. So this function here is the profit of x for a monopoly. We'll define a monopoly, but I think we all kind of know what a monopoly is. A monopoly is when there's one seller, right, and everyone else, they're all buyers, right? And so you've got a monopoly on a market. It means you are the only provider of that thing. Right? ICBC, I don't think is anymore, but it used to be, right? Car insurance, we had to buy it through ICBC. There was no other option. Now there's something weird going on. I don't know. Just stay away from that stuff. No, I don't know. I still go through ICBC, I think. Couldn't tell you. But anyway, so that would be an example of a monopoly, right? And so what happens is that they've got all of the market, right? And so as we're charging a price, right, the demand goes up and up and up, and we can still keep producing things until we reach a point where the thing that we're selling is too expensive. So people kind of hold off on buying it, right? And so we want to hit this, this sweet spot, right? Because here's the profit, right? We actually don't want to be on this side where the profit is decreasing, right? When we could be up here. Right? And so up here at the peak, right? This is our maximized profit. Very top, right? What this is, and just as a fact, the slope of the tangent line here is 0. in fact, the slope of a tangent line at any peak or valley is 0. So we use that fact to say, well, we can find the derivative of this and force the derivative to be 0 because that's this point. Right. And then we can say, well, then I can find the value of x that makes that happen, and that's where I've maximized my profit. So it all stems back to here. The slope of the tangent line is 0. Here's another little fact. The slope at any peak or valley of the tangent line is 0. The slope of the tangent line at any peak or valley, I'll put that in brackets because a top or a bottom, right? Wherever it changes the curvature, right, from going up, up, up to down, 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 there the slope and the derivative will be 0. So the slope of the tangent line at any peak of a function will be 0. So what we're going to do first, we'll say to maximize a function, your first step, we'll do this in general because that's what's on your practice test, question 2, maximize this function, right? It has no mention of a profit function or anything like that. So you're just going to maximize that function. So question 2, you're going to follow these steps. First step is find the derivative. So that's the general formula for the slope of the tangent line. Second step, set the derivative equal to 0. I guess I should write that out, not get so lazy. Equal to 0. And then your third step is find the value of x that makes the derivative 0. Find the value of x that makes the derivative 0. Basically solve for x. This is the x that will maximize your function. This is the x that will maximize your function. Let's do example 77. Pretty sure I don't have a picture of it, I don't think, because I think it's just quick numbers that I'll just write down for you. Let me just confirm here. Let f of x be negative 5x squared plus 250x minus 500. Find the point where f prime of x is 0. So what we're going to do, right, is we're going to find the derivative of f of x. And so we'll start there. F prime of x is negative 5 times 2x to the power of 2 minus 1. Just jumping straight to the derivative, where I've just given it a bump, and I imagine bringing all these powers down in front. Plus 250. X goes away, right? All the x's decrease by 1 power, so 250x just becomes 250. And negative 500 just goes away, disappears. Right? So what we get, our derivative is negative 10x plus 250. Much nicer to deal with. So now, set f prime of x equal to 0, but f prime of x is also equal to negative 10x plus 250. Oops. So now we can solve for x, right? And just bring the 10x over. So we've got 10x is 250. So x must be 250 divided by 10. So x is 25. As a follow-up question, right, because if you're looking at question 2, it just says maximize this thing, right? I'm not just looking for the x that it maximizes at, right? I want to know what is the maximized value of f of x. So what is the maximized value of f of x? So here, we know that at x equal to 25, that's when we reached our peak, right? That's our maximized point. So now what we do is we take the original f of x, right? Because that's the one that we're trying to maximize. We only had to find the derivative to get to x equal to 25. Now we can go back to that original function, plug in x equal to 25, and that's your maximized value. Right? So what we're going to do is we're going to find f of 25. F of x, just so we have a reminder of it, was negative 5x squared plus 250x minus 500. F of 25 then must be negative 5 times 25 squared plus 250 times 25 minus 500. I didn't do these beforehand. So we've got 25 squared times 5 negative 3125 plus 250 times 25, 6,250 minus 500. So I'll do minus 500 minus 3,125. So it's maximized to 2,625. Okay. So therefore, f of x is maximized to 2,625 at x equal to 25. Right, so there's two components. First, you have to find, okay, what value is it maximized at? And then what's the maximized value? Any questions about that? Cool. So let's apply this to the monopoly. So 3.4 is on monopoly. So just to define it, we've already talked about it, but a monopoly is when you have many buyers. Oops, spell it right. Oh, goodness. And only a single seller. Just so we have it, so we can look at it. Recall that we said, okay, if we have something like this, where we have the profit on the y-axis and just x on the x-axis, monopolist profit function, profit of x, might look like this. And then we said here, at some value of x, we've got this maximized profit. Here, the derivative is 0. So how these questions are going to go, they're going to be very similar to question 4 on your practice test. Notice that I've given you the total revenue and the total costs. With that information, it looks a little different than what we've been seeing before, right? But with that information, we can develop a profit function. So given the total revenue and total cost for a monopoly, we can set up the profit function. In fact, for any situation, right, we'll just use it usually for monopoly. So given the total revenue and total cost, we can set up the profit function. Set up the profit function. Because just like we said in our review, right, the profit of x is on your formula sheet as the total revenue minus the total cost. So instead of having to figure out what C and P and the fixed costs are to develop our profit function, now I'll just tell you, here's the total revenue, here's the total cost. You can smush those together to find the profit function. It's a little bit easier, I think. So here, I'll outline the steps again, but the steps are going to be very similar to what we just did, right? We're going to find the derivative, set the derivative equal to 0, right? The only difference is that now we're talking about the derivative of the profit function, right? Very specific to the profit function. Whereas earlier we were just talking about any function, how do we maximize it? So if we want to maximize the profit, first step, so these are the same steps as before, just specific to the profit function. Take the derivative of the profit of x. Step 2, set it equal to 0. Set it equal to 0. Right? Forcing it to be, okay, well, I want to know what x value puts me at the top. Right? At the top, the derivative is 0. Right? So I force that. Step 3, solve for x. X will be the maximizing output, right? How many of these things do you need to sell and produce to maximize your profit, right? So it's kind of like, okay, well, if we know x, then we can figure out what the profit will actually be, right? What the maximized profit is. So x is the maximized output not the maximized profit, but the maximized output for use x from step 3, of course, to find the profit of x. In original function. Right. If you try to plug it back into the derivative, you'll just get to 0 again because you force the derivative to be 0 to solve for this x. So if you plugged it back in, you would just get 0. Right. So that won't work. So do I have an example of this or what? 112, I'm thinking. Yeah. So example 112. Suppose that the total revenue, TR, is given by 100x minus x squared. Okay. So far, that looks fairly similar to question 4 on the practice test. Right? We're given the total revenue and the total cost here, and the total costs are given by 40x. Then, determine the monopolist's profit maximizing level of output. That's like part A on your practice test. Okay. And then what's the profit at this point? So I'm kind of guiding you through it. Right. Part B, what's the maximized profit? Right. So what we're about to do is very, very similar to question 4 on the practice test. So here's what we're given, that the total revenue is 100x minus x squared, and the total cost is 40x. I'll say find profit of X. That's kind of your first step. So from your formula sheet, you have profit of X is the total revenue minus the total cost. That's on your formula sheet. Now we can swap those out because we know those, and I'm going to put brackets around each of them just to indicate that this is one thing and this is another thing, just so I'm not messing up negatives if they're there. So we've got 100x minus x squared minus 40x. Just putting those in. No worries. We're almost done anyways. We're almost done, guys. You can be joining him and feeling good. Better. No fun when you're not feeling well. So here, right, we've got, now we can collect like terms. We can simplify this a little bit. All right, so if I just get rid of the brackets, first of all, then I get 100x minus x squared minus 40x. I can collect these x's, right, and say that 100x minus 40x puts me at 60x. Oops, not 6, but 60x minus x squared. Right. So there's my profit function. Nice. So step 1, find the derivative of profit of x. Okay. So we're going to say the profit prime of x. So now, right, we just do the same thing, right? Give it a bump from the right. And so 60x, the derivative of 60x just becomes 60, right? The x disappears. So we get 60 minus, and then we bring that 2 in front, 2x. So there's the derivative of the profit function. I told you it wouldn't be so bad. We're doing fake calculus, but you're doing it. Doing calculus. Second step, set the derivative equal to 0. And then I'm also going to do the third step, solve for x. So I've got the profit prime of x. I'm forcing it to be 0, but it also is 60 minus 2x. So now I can swap things around, right? Solving for x. So I get 2x is 60. So x must be 60 divided by 2. So x must be 30. Right? So the profit maximizing level of output is 30. Therefore, what part was that? The profit maximizing level of output is x equal to 30. So now our fourth step, so now we found that first part A, let's call it. Right. Now we want to find what is the maximized profit. Find the maximized profit really just find the profit at 30. So remember our original profit function, profit of x was 60x minus x squared, I think, right? So the profit at x equal to 30 is 60 times 30 minus 30 squared, which is, I'm just going to double check this, 1800. 60 times 30 is in fact 1800 minus 30 squared is 900. 1800 minus 900 is 900. That's why I had to double check, but it is. Not that, but that I'd repeated a number somewhere. So the maximized profit is 900 of whatever you're talking about, right? Maybe it's 900,000 million, who knows? But any questions about that? So like I said, it is this kind of new weird thing, but we're only doing it for test 1. So just kind of figure it out for test 1, and then it's not going to come back for the final. Okay? I can promise you that. How about? No questions? Okay. Come grab a practice test if you don't have one already. Otherwise, I'll see you for the review on Wednesday. Cool.